The total power in a three-phase system is, as you would imagine, the sum of the power in each phase of the system. So we're looking now at the star system. So the total power in a star system will be the power in the red phase plus the power in the yellow phase plus the power in the blue phase. All right, so one way of working out power, and this is important especially for systems where you can have inductors and capacitors. One way of working out power is by using this formula, right? So the formula for single phase power is V times I times cos theta. And theta is the angle between the voltage phasor and the current phasor, right? And I think I've shown you some of that when we look at waveforms. So if we were to look at the power in one phase using the VI cos theta, it would be the voltage across that phase, VR or VRN, the current through that phase, IR, and then the cosine of that phasor difference between those two phasors. That angular difference. All right. So that angular difference now is the angle of the voltage phasor minus the angle of the current phasor. All right. So that is written down here. The voltage phasor angle minus the current phasor angle for the red phase. And we can write similar relationships for the yellow phase and the blue phase. All right, so in general then, the total power in the star connected system would be the sum, as I said before, sum of the power in each of the phases, and we have written them out here now. So VRN IR cos theta R plus VYN IY cos theta Y plus VBN IB cos theta B. All right, so that is the general formula for power in a three-phase system. But when we get to a balanced system now, we can actually simplify this so that it look a little bit neater. All right, so for a balanced star connected system, remember that the magnitude of the phase voltages are the same, right? So the magnitude of VR equal the magnitude of Vy equal the magnitude of Vb, and let's just call that V phase. So it's the magnitude of the phase voltage. All right, and we also, from last week, can remember that for a balanced star system, the magnitude of IR would be equal to the magnitude of IY equal to the magnitude of IB. And so we call all of those the phase IP for I phase, the phase current. All right. We also know that for a balanced system, based on what we did last week, the magnitude and angle of the impedances are the same in each phase, right? So ZR angle theta R would be equal to ZY angle theta Y equal to ZB angle theta B equal to some impedance at some angle. So all of these are equal, right? And that made our system balance. All right, so basically I've summarized all of these. So I can rewrite now the general equation for the power, the total power, as so substituting where I have VRN or VYN or VBN, I substitute VP. Where I have IR, IY, and IB, I substitute IP. And where I have the cos theta R, cos theta Y, and cos theta B, I substitute that for cos theta P. Right? So when you look at this now, you realize that you're adding three of the same things. So the total power in a balanced system is 3 V phase, I phase, cos theta. And this cos theta here now is the angle between any particular phase voltage and its corresponding or its associated phase current. So PT is equal to 3 VP IP cos theta P. All right. So I can write this general balance formula for using the phase values in terms of the red phase, right? So I could choose any phase. But if we consider the red phase, then this total power could be written as P equal to 3 times VRN, so it's the red phase voltage, times the red phase current, times the angle between these two phases, right? And again, similar equations can be written in terms of the yellow phase and the blue phase. So for a balanced star system, that is the formula. But I want you to remember that I phase is equal to IL, and V phase is also equal to VL over root 3. So I can rewrite this equation in terms of line values. So if I substitute for VP, it becomes VL over root 3. And if I substitute for IP, it becomes IL. All right, there's no substituting for cos theta P though, right? So I remember cos theta P is the same. For a balanced system, it's going to be the same in each phase. So we're still good. So PT in terms of line values then is equal to root 3 VL IL cos theta P. All right, so two ways of writing it for a balanced system: 3 VP IP cos theta P, or root 3 VL IL cos theta P. So respectively, we're writing in terms of phase values or line values. All right, so basically this is summarizing what we have done so far with the power. Let me make sure I didn't leave out anything. Right, so for the, it's basically summarizing what we have. So you have all of that on one page. General formula up top, and for specific case where you have a balanced system, it's that or that. All right. Any questions so far? Are we good?
Sir, question not in regards to this specifically, but you said that you would give us like the notes like before class so that we can review it and so that when we come to the class we can have a little bit more prepared. But I checked and I did not receive, so just kind of checking on that.
Oh yeah, man, I will do that. Sometime because I have so many classes going on, I forget what I haven't done. All right, but so if you see like the morning you don't see anything, just send me an email and say ask what's the thing. I won't feel anyway.
Okay, all right, sir. Cool.
All right. Yeah, but yes, I was telling myself that I need to organize myself a little bit better so that I know what I can tick off what I've done. All right. So, but thanks for the reminder.
Yeah, man.
All right. So I guess everybody is okay with this. All right. So I want to look at how we came about naming the voltages, the line voltages, in the way we have. Why RY and not YR? Why BR and not RB? Why YB and not BY? All right. And the answer has to do with something that we call phase sequence. So the sequence in which the phases are actually rotating in the star system. All right. So recall something that we did last week. Maybe this should have been done last week also, but all right, it can work right here also. All right. So remember that the phases are rotating. So imagine all of these now as three spokes of a bicycle wheel. All right. So you have your bicycle wheel have three spokes, and when you turn, when it's turning around the axle, all the spokes are rotating. Now, if you're standing where omega is, if you're standing, your eyesight is here, your eyes are here, and you're looking straight across, the spokes are rotating, the wheel is rotating, so the spokes are rotating. The first thing you will see coming up is the red spokes. Then after that, coming up behind it would be the yellow spokes, and then after that would be the blue spokes. So just picture that going. So the phases are rotating, and they are rotating in the anti-clockwise direction. So opposite to the way the clock could move, the phases are rotating. All right. So they are rotating in the order or sequence: red, yellow, blue. Right? And they are going anti-clockwise. So this sequence will continue as long as power is on. Right? So it is red, yellow, blue, red, yellow, blue, red, yellow, blue, going in the anti-clockwise direction. Now the line voltage is measured between any two adjacent lines, right? So it's RY. So that's why we have the VRY. Then it would be YB. That's why we have VYB. And then the next one now would be BR, VBR. So voltage between R and Y, VRY, between Y and B, VYB, and between B and R, VBR. Now, if we had changed these round, the direction in which the phasors are turning, the phasors are located would be the opposite, right? So this is the particular order that we have them. So just as how the sequence is going, we connect up adjacent letters or phasors to get the line voltages. All right. Now, this is something that is of some importance to you, but probably of major importance to people who are doing power systems. For a balanced three-phase system of phasors, they have two important properties, right? One, we think about the direction of rotation. It could be clockwise or anti-clockwise. And we think about the sequence of rotation. It could be red, yellow, blue, as we showed you before, or it could be red, blue, yellow, right? So in our case, though, we are using red, yellow, blue, and the red, yellow, blue is considered to be the positive sequence. So in some problems you might see in your textbook, they might say, boy, the rotation is positive sequence, right? They are basically telling you that it is rotated in the order red, yellow, blue. All right. So for this module, we are using the positive sequence of rotation, red, yellow, blue, and the phasors will be moving in the anti-clockwise direction. So generally our measurement is from 0 around. Get to the blue here, it will be 120 degrees. Get to the yellow here, it's 240. So that's why you see 240 associated with the yellow phase and 120 with the blue phase. All right. All right. Any questions on the sequence thing? So it is important, let me just say this too. It is important, and you can see a practical demonstration of how the sequence or how the rotation can change. If you change around two terminals of say a motor, let's say it was rotating in the clockwise direction before, and you switch around any two terminals, you will find that the motor will actually start to turn in the anti-clockwise direction, right? So you can see the importance of rotation, knowing the rotation, because you may connect a machine that should be going in a particular direction. If you don't connect it properly in the right sequence, then you may have the machine coming back in the reverse direction. Think about a cutting tool machine, and you can imagine what kind of disaster that could be. All right, so in the era of power system operation, it is very critical. If they are going to do some maintenance, they would actually check the rotation before they take the circuit out for maintenance. And when they finish maintenance, they check the rotation before they start to put on back the load, just to make sure that it is what it was before. All right, so point to note. All right, let us look at the delta system. All right, so delta is also called mesh, and it is also the symbol, the Greek letter delta, is used also. You can notice the similarity with this circuit here over here. All right, now the loads in the delta connected system are ZRY, ZYB, and ZBR. All right, and again, now the loads are connected in between two line terminals in this case. So ZRY is connected between the red line and the yellow line. ZYB is connected between the yellow line and the blue line. And ZBR is connected between the blue line and the red line. Right? Now remember that loads are connected in the phases. Loads are connected in the phases, right? So the voltage across the phases is a phase voltage. Now, if you look at this, the voltage across R and Y is VRY, right? So that is the voltage across here. Put one terminal of the voltmeter here and another terminal here, and you'll be measuring the voltage across here, VRY. If I move the pointer out to here, and from here to here, I'll be measuring the same thing, right? So VRY is across ZRY, VYB is across ZYB, and VBR is across ZBR, right? Now remember that, so those are the phase voltages. But remember also that the line voltages are the voltages between any two lines. So the line voltage across here is VRY also. And across here is VYB. And across these two outer ones here is VBR. So we can see just from observing this circuit that the phase voltage across here is the same voltage across here. The phase voltage is equal to the line voltage. All right. So for the delta circuit, VL is equal to V phase. All right. Now, the reference phasor for the delta system is VRY. So it has the R in there. So it's the phase voltage. So the reference phasor for the delta connector system is the phase voltage, VRY. All right, so therefore we would write VRY as V angle 0, and VYB as V angle 240, VBR angle 120 degrees. All right. So these phase voltage would also define the line voltages, right? All right. Now let us look at the phase currents. So the phase currents now are the currents that are flowing through the load, right? The loads that are flowing through the load are the phase currents. All right. So IRY flows through ZRY. IYB equal will be the phase current flowing through ZYB, and IBR would be the phase current flowing through ZBR. All right. And the line currents, as before, flows on the lines, flows through the lines. So IR would be flowing through the red line, IY would be flowing through the yellow line, and IB would be flowing through the blue line. And remember now, the lines are connected to the source. So the lines connect the source and the loads. All right. So the line currents are IR, IY, and IB. And as we did before, we want to find the relationship between line currents and phase currents, because we can see that they are going to be different. All right. So that is our question. Now, what is the mathematical relationship between line currents and phase current for the delta system? All right. So that relationship can be determined by using Kirchhoff current law at each of the nodes. So this is a node. So this point here, mark R, is a node. This point here, mark Y, is a node. And B is also a node. All right. So we can recall what Kirchhoff current law says. Anybody want to shout that out quickly? What Kirchhoff current law says? All right, very good, very good. All right, so at node R, what do we have entering the node? Just look at the diagram. Maybe
IR, sir. IR.
Right, very good. IR plus IBR going in. And what is leaving then? IRY. All right, so that's why we write this here, right? So making this line current now the subject, IR would be equal to IRY minus IBR, right? And we can write similar equations for node Y and node B. So IY would be equal to, again, IYB minus IRY. Somebody coming in. So IY and IRY are entering into this node and IYB is leaving, right? So that's what this is saying. Similarly, for node B, IB and IYB are entering and IBR is leaving. So IB is equal to IBR minus IYB. All right, now the best way to, maybe the simplest way, maybe not the best way, but the simplest way to explore this relationship a little bit further is to use some examples. All right, so that's what we will do. All right, so first I'm going to look at an unbalanced system. And then later on, we look at a balanced system. All right, so the question says a three-phase 400-volt system has the following load connected in delta between the red line and the yellow line, a non-reactive resistor of 100 ohm. You might recognize some similarity with this question with one from last week, but this time it's a delta connected system. All right, now between the yellow line and the blue line, a coil having a reactance of 60 ohm and negligible resistance. And between the blue line and the red line, a loss-free capacitor having reactance of 130 ohm. And we are to calculate the phase currents and the line currents. All right, so to do this now, let us define our voltages. All right, so the system voltage was 400, and we know that VL is equal to V phase. So the phase voltages are VRY 400 at angle 0, VYB 400 at angle 240, and VBR 400 at angle 120. And the impedances are ZRY 100 at angle 0, ZYB 60 at angle 90. It was an inductor, right? Reactance, right? It was a, yeah. A coil, right? I was looking for the right word. So a coil, which tells you it's an inductor. And the other one was a loss-free capacitor, which means that there's no resistance there. Well, losses actually take place in resistance. So there are other formulas for power. The other one that we can use is I square R, right? For per phase power. So it's VI cos theta R I square R. All right. Now for the capacitor, where is my somebody coming in? It is 130 at angle minus 90 degrees. So the capacitor would be at a minus 90 degree in terms of its phasor. All right, so we want to find the phase currents, and these are IRY, IYB, and IBR. So again, we write our formulas, VRY over ZRY. That would be equal to IRY. And we do the maths. We substitute the values. IYB is VYB over ZYB. And that works out to be 6.667 at angle 150. And IBR is VBR over ZBR. 400 angle 120 over 130 angle minus 90. When I put it in the calculator, I get this. But if I did just do the straight maths, I would get this, right? When you're dividing, you just bring this up and add. So, no, when you're dividing, you subtract, sorry. You bring this up and you subtract minus 90. So it becomes 210. All right. So those are the phase currents. Those are the phase currents. And we need to find the line currents. All right. Now using the relationships that we had developed before. All right. And I just write them back here so that you can have the diagram here so you can see it. IR would be equal to IRY minus IBR, and IR up here is 4 at angle 0, and IBR is 3.00077 at angle 210. So I'll get the current in the red line is 6.84, and that would be at angle 13 degrees. All right. I kept this data up here so that you can easily recall what we had worked out before. So IY is, again from the diagram, IYB minus IYR. As I mentioned from the diagram, it is very important that you label your diagrams then properly, because if you incorrectly label your diagram, but the formulas are like this, you will not get it right, because I'm going to be looking at your circuit and see how you label your circuit. So make sure you label it properly so that it makes sense, the equation makes sense, and it's not something that just comes from memory. All right, so make sure you label. So labeling would mean labeling all of the line currents and phase currents, if you're looking at currents, and phase voltages and line voltages, all of that. So properly labeled diagram must correspond to the equation, must correspond to the labeling of the diagram. So it's don't just memorize the equation and write down and your diagram don't look good. And if there's no diagram and an equation is there, I wonder how you get it. So you need to show me how you get it. All right. So let's go to, so we had worked out what IY is equal to. 10.327 at angle 161.17 degrees. All right. For IB, line current in line B, again, we just substitute the values. IBR is that, and IYB is that. And we get 5.78 at angle minus 57, or if we want to write it in terms of the positive direction, rotating in the positive direction, it would be 5.78 at angle 302.54. All right, as I said before, if you leave it at this, I don't have a problem. The 5.78 at angle minus 57.46, I wouldn't have a problem. All right. So either way you write it would be okay. It's all right for me. Just bear in mind though that angles are considered positive when they're moving in the clockwise direction, in the anti-clockwise direction, and negative when they're moving in the clockwise direction. All right. So yeah, so that's it for that problem. We were asked to find just the phase currents and the line currents. All right. And you can see that the values bear out the fact that it is an unbalanced system. All the magnitudes are different for the phase currents, and the angles are not 120 degrees apart. This one is 150 degree apart. This one is about 60 degree apart between these two. So clearly not a balanced system. And similarly for the line currents, We had this one at 5.78, IY at 10.3, and IR at 6.84. So clearly not a balanced system, right? And it has to do with the loads, because we have our voltage has been balanced. Remember, we have decided to use our voltages as balanced. All right, so that is for an unbalanced delta system. Any questions on this before we get to a balanced one?
So there's been some time for write this one.
Say that again?
Just give me a minute to write all this.
Okay. All right, I will send this to you, you know. I think I will post it this evening.
All right.
All right, but no, you take your notes because it's good to make your own notes. All right, so tell me when to go.
Yeah, man, go ahead.
All right. Right, you can keep it. You can keep it. Yeah, so just bear in mind how they are measured though. One is measured, the negative values would be measuring clockwise. So starting at the reference and going clockwise. And the positive values now would be starting at the reference and going anti-clockwise. You'll end up at the same point for both of them. All right. All right, now let's look at a balance system. So this time, 3 loads, resistances, 30 ohms are connected in delta to a 415 volt 3-phase supply, and we again should determine the phase current and the line currents. All right. So again, the voltage that is given in the problem is usually a line voltage, and we want to write our phasors, and our phasors are phase voltages, right? So VRY is our reference, so it's at 415 at angle 0. VYB 415 at angle 240, and VBR at 415 at angle 120. And the impedances are the same in each phase. 30 at angle 0. All right, so we should find the phase currents. And again, now IRY is VRY over ZRY. Substitute the values. So 13.833 at angle 0. IYB, formula VYB over ZYB. So 415 at angle 240 over 30 angle 0. So 13.833 at angle 240. And IBR is VBR over ZBR. All right, so you can see that the phase currents are balanced, right? So as we expect for a balanced system. All right, I should point out something to you. When you're solving a problem, I look for the formula. So I expect to see the right formula. I expect to see the right data being applied. And I expect to see the right answers. So you get marks for all of these, you know. So right formula. So always write your formula. And make sure you write the right formula. Make sure you put in the correct data in the formula. And try to get the right answer. All right. So you get marks for all of these. All right. So my marking scheme is fairly straightforward. A mark for formula, a mark for the right values in the formula, a mark for the right answer. All right.
And diagrams too, sir.
Yeah, especially you should always draw a diagram. Always draw a diagram and label it properly. Say that again. Yeah, the expert as yet. When you expect to be an expert? Yes, it gives you a real good pictorial view of what you're working with. And it helps me who is marking the paper to understand what you are doing. Suppose you're doing something a little bit unusual from what I expect, but when I look at your diagram and see how you set out your procedure, I will be able to follow what is going on. So a diagram is important in helping me to see how you come up with your equations and all of that. But you'll be an expert by next week.
Sir, just a quick question. I guess we kind of missed something. All right, in terms of like the directions of the voltage where you have VRY is 415. VY, I guess I'm kind of lost at where it says VYB is equal to 240. I'm trying to follow the direction, right? You said that it's anti-clockwise, correct?
Right, right. All right.
So,
you remember when we were looking at the star system and we had a VR at 0 and VY at 240 and VB at 120?
hold on, sir. You can break up a little bit. Repeat that again for me.
Yeah. I hope it's not anything with my transmission.
Oh, sir, it's his.
Oh, okay.
Yeah,
All right.
All right. Yeah, I can hear you now, sir. Go ahead.
All right. So remember when we were looking at the star system, VR was at angle 0, VY was at angle 240, and VB at angle 120. Right. You remember that?
Yeah. So still based on the same star system?
No, it's not the star system, no, but it's the same phase difference between the phasers. Remember, a balance system going to have 120 degrees between the phasers, right?
Right, right.
So they are going to be located like this.
Okay, so how you explained it, the angle difference in the star system basically is the same that we're using here, right? So
right.
Okay.
Right. Okay. It's just that the subscripts now are different. But these are still so when we're using the star system, we set out the red phase at angle 0, red phase voltage at angle 0, the yellow phase voltage at angle 240, and the blue phase voltage at 120. Okay. We're doing the same thing now with the phase voltages for the delta system. Right, so we're using VRY at angle 0 and VYB at 240 and VBR at 120. Okay. So it's a very important question, and yes, you should take note.
Okay. All right.
All right. All right. So we had gone through that. No, we're now to find the line currents. Right. So the line currents are IR, and line currents based on the diagram is IRY minus IBR as before, and we're substituting these values now. So IR works out to be 23.96 at angle minus 30 degrees. All right. I think I left it there. I didn't bother go to the positive. Similarly for IY, it's 23.96 at angle minus 150 after we substitute the values. And IB, 23.96 at angle 90 degrees. All right, so if you look on it, you will see that all the phase voltages have the same magnitude, and they are 120 degrees apart. And all the line currents have the same magnitude. And if you look at this, between here and here is 120 degrees. Right? Yes. No, it depends on what you're required to do, right? Like in this one, they ask you to find the line currents. Right. So it's not only the magnitude now, but they want the angles also. All right. But I will what you're saying we will use later on also, right? So it depends on what is being asked, right? So if you see currents, you know, so you want all of them, right? And here for teaching purposes too, it also shows you that there's a 120-degree difference between each of these phases. Same magnitude, 120 degrees apart. So they are balanced. All right. So I've rewritten that. And we're looking now at the voltage and current relationships. That's what we're doing, right? In a balanced delta system. So if you notice that the phase currents have the same magnitude, IP is 13.833, and the line currents, IL, have the same magnitude, 23.96. So if we divide the magnitude of the line current by the magnitude of the phase current, we get 1.732. All right. Which is equal to root 3. All right. So I think you will see where I'm going. So therefore, IL, the magnitude of the line current, is equal to root 3 times the magnitude of the phase current for a balanced delta connected system. And that is usually just written as IL is equal to root 3 V phase. IL is equal to root 3 I phase for a balanced delta system. All right, so a little bit of summary here, covering all that we have looked at so far with the delta system. For a delta connected system, VL is equal to V phase, and IR from this diagram equal IRY minus IBR, IYB minus IRY, and IBR minus IYB. And for a balanced delta connected system, IL is equal to root 3 I phase. All right, so these are some relationships that you will be applying, and you'll become an expert in no time. All right. All right. So, any question on what we have done so far? Any other questions?
No.
No, sir.
All right, good. All right, so now we're going to look at the power in the delta circuit. All right, so the power, so the total power drawn by a delta connected load is given by the power, the sum of the power in each of the phases. So power in the phase RY, power in the phase YB, and power in the phase BR. All right. As before, basically, as we did with the star system. So PRY would be equal to VRY times IRY, so phase voltage times phase current, times the angle, the cosine of the angle between the voltage phasor and the current phasor. And you can write similar equations for the power in the blue phase. Right? VYB times IYB times cos of the phase difference between VYB and IYB. And PBR, power in the blue-red phase over here. VBR, voltage across that phase. Current through that phase impedance. And the cosine of the phasor difference between these two phasors. So the total power can be written out, just put this way. All right. Now remember now, for a balanced delta system, VRY is equal to, so this is the general formula, right? And if we look now at a balanced system, the magnitude of the phase voltages are the same, and they are equal to VP. The magnitude of the phase currents are the same, and they are equal to IP. And the angle between phase voltage and phase currents are the same for each phase. All right, so let's call that theta P. So just to reiterate here, this formula up at the top of the page is the total power in a delta circuit, whether the system is balanced or not. Right? For the balanced system, we're going to be substituting for the phase voltages in terms of VP, and for the phase currents in terms of IP, and the phase angle between voltage and current phasors as theta P. So rewriting that, we get VP IP cos theta P plus VP IP cos theta P. All right. And again. So the total power for a balanced delta system now is 3 VP IP cos theta P. All right. And you will realize that it's the same formula as before. Also, for a balanced delta circuit, we know that VP is equal to VL and IP is equal to IL over root 3. All right, so if we want to write them in terms of the line, the total power in terms of the line values, we substitute for VP and IP in this formula up here. So we get PT is equal to 3 VL and IP is IL over root 3 cos theta P. So the total power in the balanced delta circuit can be written in terms of line values, root 3 VL IL cos theta P. Again, similar to what we had for the star. All right. So I'm going to give you a chance now. I want you to solve this problem. 3 similar inductors, each of resistance 10 ohm and inductance 0.019 Henry, are delta connected to a 3-phase 400 volt 50 hertz supply. Wanted to find the value of the line current, the power factor, and the total power in the circuit. All right. So I started you off, but I want you to continue. So I'm going to give you about 10 minutes. Maybe that's too much. But 10 minutes to solve this. All right. Phasor. Therefore, the voltages are this: 400 VRY, 400 at angle 0, VYB, 400 at angle 240, VBR, 400 at angle 120 degrees. All right, so this is something that somebody had asked me about earlier. Now, we're calculating the phase currents, but since the system is balanced, we only need to calculate for one phase. All right. In this case, they had said find the line current, the value of the line current. So we only really need, since the system is balanced, to find one line current. All right. And when you see them write it like this, like the line current, they really just want the magnitude. All right. If you give magnitude and angle, though, you will be more accurate. But maybe not necessary for the way how the question is asked. That's why I said earlier, it depends on how the question is asked. All right. So we find the current for one phase, IRB. And to find IRB, then we'll IRY will be VRY divided by ZRY. So VRY divided by ZRY, so find IRY. And it's 400 at angle 0 divided by the 11.646 at angle 30.83. So that phase current now works out to be 34.347 at angle minus 30.83 degrees. And you know, current is measured in amps. All right, so we know what the IRY is. So therefore, we know that the magnitude of, since it's a balanced system, we know that the magnitude of the phase currents is equal to 34.347 amps. All right, now the question asks us to calculate the line current. So for a balanced delta system, we know that the magnitude of the line current is equal to √3 times the magnitude of the phase current. Right? So IL is equal to √3 I phase. So √3 times the 34 give us 59. So the magnitude of the line current is 59.491 amps. All right. So that would have answered that first part of the question. Yes. Right. I mean, no, you don't need to, like in this case. No, you wouldn't need to. All right. So as I said before, make sure you really pay attention to what is being asked. So you answer what is being asked. All right. Now we should calculate the power factor part 2. So we should calculate the power factor. All right. So there are 2 ways that we can calculate the power factor. One is from the phase voltage phasor and the phase current phasor for any particular phase. All right. And then the other way is to use the impedance triangle for the load, for the balance load. All right. So if we use the phase voltage phasor, VRY is at angle 0 and IRY is at angle minus 30.83 degrees, right? So the power factor is equal to the cosine of this voltage phasor minus the current phasor. The angle for the voltage phasor minus the angle for the current phasor. All right, that's what power factor is. The cosine of the angle, the phase angle between the voltage phasor and the current phasor. Now, mathematically, that is equal to cos the voltage phasor angle is 0, and the current phasor angle is 30.83. So therefore, doing the math here, minus minus gives you a plus. 0 minus minus 30 give you 30. All right, 0 plus 30 is 30. And the cosine of 30.83 is equal to 0.859. And it's lagging because the current here is minus, right? So we know that the current is lagging the the current is lagging the voltage phasor for the particular phase. All right. So when you're quoting power factor, you must state whether or not it is lagging or leading. So in this case, if it's not unity, it must be either lagging or leading. So in this case, the current is lagging. This minus sign mean for the current means that it is lagging the voltage phasor. All right, so the power factor is 0.859 lagging. All right, so this is explaining what I was saying before. All right. All right, the other way of determining the power factor is to use the impedance triangle for the load. So the load is balanced, is the same load in each phase, right? So from the triangle we had, this is the impedance triangle, R plus JX give you Z, R plus JXL. All right, so the 10 R equal 10, and the JXL is equal to J 5.969. So Z is equal to that. And this angle is the angle at which Z is equal to, right? So if you want to find the power factor of this angle, you could just look here and say cosine of this, or if you want to use a triangle, you say cos theta would be R adjacent over hypotenuse, R over Z, and you get back the 0.859. Now, because this is an RL load, okay, inductive load, we know that the power factor would be a lagging thing, right? So this now you have to use your intuition. You find the angle, you find the value of the power factor, but you will now have to use your intuition now to say yes, well, it's lagging, right? If you use this one though, the minus angle with the current will tell you that it is lagging. All right, so one is a little bit more straightforward, but one is easier, but you have to use some intuition. So this one may be a little bit more tedious to do, but it tells you exactly what is happening. And when we talk about lagging or leading, we are looking at what the current phasor is doing with respect to the voltage phasor. So lagging is what the current is doing. The current can either lag the voltage phasor, as in this case, or it can lead the voltage phasor, as in the case of a capacitive circuit.
Sure.
Yes.
In a practical sense, what does the power factor represent?
This formula here tells you, right? This tells you. Right. We want to see, basically you want to know whether or not your system is operating. Ideally, you want your power factor to be ideally 1. All right, so this is one way of determining the power factor. Another way, and we can look at it through this too, right? So one way of determining the power factor is to look at the difference between the voltage phasors, the voltage phasor and the current phasor, and you work out the cosine of that angle. Another way is going back to this, right? This value here, 3 VP IP, is actually what is called the apparent power. The 3 VP IP, or the root 3 VLIL, is the apparent power of the system, right? So, and then the PT is the real power. I think I have a power triangle thing here also. So if you look at this now, you will find that the power factor is also now the ratio of the real power to the apparent power. So the power factor is giving you a measure of how much work you can get out of a certain amount of apparent power. And when you say apparent now, you apply a certain amount of voltage and you see a certain amount of current flowing. So you expect that in all practical purposes, you expect that whatever you put in, you should be getting out. But the power factor now is saying no. What you get out is actually some fraction or factor of what you actually put in, right? So it is a comparison of what is expected with what is actual.
Okay.
I don't know if that make it clear to you, but looking at this formula, you can see it. Okay.
Sir, so basically, right, because we know that systems we can only use the real power, right? The real power is actually what we use. So, to my understanding, based on what you just explained, the power factor is a measurement of what percentage of the actual power you can use, right?
Right.
Okay.
All right. So there is later on when we get down to transformers, and if you could do drives too, you will see actually machines are actually rated in terms of their apparent power, right? And what they actually do now in terms of how much you can actually get out of them is going to be dependent on the power factor at which they are operating. So the power factor basically, if it is a purely resistive load, then the power factor is unity, and whatever you put in, you will get out, right? For say a purely resistive load. For inductive RL or RC load, you will not get everything that you put in, because some of that apparent power, and we'll discuss that in a little while, some of that apparent power is going to be used up in the resistive circuit, right? So it's also a measure of the amount of reactive power usage in a particular load. All right, but I don't want to complicate it more. If you use this formula, and when we get to the impedance, the power triangle, you will see it. So one way of determining it is to say, boy, cos theta is equal to the real power over the apparent power. Another way is to look at the difference between the voltage phasor and the current phasor and find that angle, the cosine of that angle difference. All right. Okay. All right. The last thing that they asked us to do for this problem was to find the total power, the active power input to the circuit. All right. So what we're actually doing is working out the power used by the load, right? Because although it's the input to the power input, the source is what will be putting in the power, right? And between the source and the load, you can actually have some power drops, right? But we're ignoring those and considering just what is happening. Assume that whatever the source outputs is what the load will be consuming. All right, so we get back to our formulas for a balanced load, and the system is balanced as we have been seeing. The total power is 3 V phase I phase cos theta, or root 3 VLIL cos theta. So if I use the phase parameters, PT would be equal to 3 times the 400 times the 34 for the phase current, and the power factor was 0.859, right? And if I use the line values, root 3 VL, and the IL is the 59.49. So you should get the same answer. Differences in slight differences in answers may be due to the extent of the rounding off. But you should expect same kind of values if there's no rounding off. All right, so that's for that problem. Oh yes, I had wanted, right, I was talking about the power triangle. So we had looked at the power triangle a while ago. And power factor can be determined from the power triangle, as we were saying, right? The cos theta.
Can I go back 2 seconds, please?
You mean in what I said, or back to the previous slide?
Previous slide, sir.
Okay, yeah, that's easier because I couldn't remember what I said 2 seconds ago.
Thank you, sir.
All right. Good. All right, so the power triangle, right, for an RL load is shown here. I don't know what I had said before. But anyway, what we're talking about now is the power triangle for an RL load. So this is what the triangle look like. Notice now Q is going vertically up, right? The real power P would be on the 0 axis. So 0 degrees here. This is going up 90 degrees on the J axis. So P would be on the real axis. Q would be on the imaginary axis and the positive pole of that axis. And the sum of P, the phasor sum of P and Q will give you the apparent power S, right? All right, so in terms of phasor sum, S is equal to P plus JQ, right? And S is the apparent power. So basically it is V times I for a per phase system. Whereas power would be VI cos theta and Q would be VI sin theta. All right. Q, so sin theta would be opposite over hypotenuse. All right. And if, so this is a 3-phase S, it will be root 3 VLIL or 3 V phase I phase. Right, so Q would be S sin theta, which would be the root 3 VLIL sin theta for a 3-phase system. And you can write similar things for P. All right, so this is the impedance, the power triangle for an RL load. And a similar one for RC load. This time now the Q is going vertically down. So it's on the J, the minus J axis this time. The minus J axis. P is still real, and apparent power now will have a negative angle. Right? All right, so that's for that. These are some questions. All right, what I will do, what I will do is send this to you now, and you can start working on these for. I will post this in the classrooms, and you can start working on these for tomorrow. So hopefully you would have solved them. All right, so I'm gonna give you these to do for tonight, and we'll meet back tomorrow. We'll look at them, and I think we can look at some others also in the tutorial session. All right. Any questions? I think we can call it. If there are no questions after this, we can call it there.
No question, sir.
All right. And you're unanimous in that?
No questions, sir. No questions.
No question.
All right. Good. Good.
Yes,
Okay. We need to form some groups. I don't know if you have worked in groups before in your previous years. I imagine that many of you would be coming up through this system together. But we need some groups for writing up labs. I think for some of the labs, I'm not so sure how many people can work at a particular station, but chances are it could be one. I don't know, Mr. Campbell. You can say whether or not more than one person can work at a station.
Two would be the maximum.
2 would be the maximum.
Yeah.
Oh. All right. But still, even if you 2 work at a station, I would want groups of 4 still. So each group of 2 collect their readings and submit it. But we have one write up. So we'll have to work out how it will be done. There's one more thing I want to do before we get into the lab on 3-phase systems, and that is basically how we use the 2-watt meter method of determining the power in a 3-phase system. So when we do that, after that, I think we can do some lab work. There are about 40 of you in the class right now. I understand it might go up to 50. So the 2-watt meter lab usually takes up most of a 3-hour session. So it might be a long while doing labs, stretching out, but we'll see how it goes. So you will get some more details on that, but I want to just finish doing in class the 2-watt meter method, which shouldn't take long, and then we can get into the lab. So I suspect that maybe by not next week, but maybe the week after, we can get into the lab. All right. And I suspect that some labs are, well, not suspect, but some labs will be done and recorded and sent to you so that you can do your write-up. But the 2-watt meter one is a good one to have you use in all of the instruments and seeing actually how the circuit is connected. These circuits would be what you probably would be seeing on the board in the lab. So when we're doing the 2-watt meter lab, we'll be using a delta circuit, and this would be basically how it would be represented. So this would be representing one load, A representing a load, B, common B, and common C representing a load. And then you connect wires to make the delta circuit. And in some cases, you'll be measuring voltage across a phase, and you'll be measuring current in a phase. So you would be putting a meter here, right? And you also be measuring power going into the phase, and it will be one that will have you using the ammeter, the voltmeter, and the wattmeter. So that would be a good one. and the circuit can be a little bit tricky. So
Sir,
yes.
how this will go? You have to come in a specific time, or
Right. So we will have to work out. So that's what the reason why I wanted to know the
I just
groups
have
now,
to take
so I
bus
can
come
say
here.
all right. Say that again.
I would have to like take a bus or a taxi and come to school.
All right. Where you living in?
Same time.
St. Anne's?
Yeah.
Oh.
Yeah, man.
All right. Yeah. But I don't want to shortchange you. You hands on. I don't want to shortchange anybody with that. I mean, the alternative would be to have the labs done and the results recorded and the results sent to you. So those are the two options that we have really, and most of them will be done using the option of recording and sending the results to you. But I wouldn't want anybody to say, boy, we never get a chance to do any practical work.
You can do on the weekend.
Weekend.
Weekend thing then are really
No, that won't work because the lab technician wouldn't be available, I think, on a weekend, and I won't be available on a weekend either. There are other things that take up our time.
Yeah, man, you just can't be the night session, sir.
No. In fact, our schedule says a 9 to 12 and a 1 to 4 on a Monday.
How many labs are there to be done, sir?
Normally we do about 5 or 6. So we'll probably work out. We might get through all of them where the results are sent to you and you will do the write-up. But yeah, we'll work out all of those details later on. So normally 5 or 6. All right? Yeah. I'm not sure how. Somebody asked me about dry zone already, so it's possible. I don't know. Anything possible, I guess. Dries too. Okay. All right. Well, yeah. I guess as time go on, we can see how we are a little bit more clearer.